Hello again. The previous lesson, we finished rational equations applications. Now we're moving into exponential functions. An exponential function is different from a linear function because the variable. So let's begin with the quick rules. So here are the quick rules. You can review them. We'll review at the end after we problems. So first of all, for f of x equals 3 times 2 to the power of x, we want to evaluate the function at the points given. Plot the points and state the y-intercept. So we want to evaluate by substituting for the x value in the function. So we want to start with x equals -1. So when f, I'm just going to rewrite the equation. We have 3. So that's the equation. We want to evaluate it for -1. So when we evaluate it for -1, have okay. Now what this means is 2 negative 1 means 1/2. Okay, so 2 -1 means 1/2. That's essentially 3 times 1/2. So f of 1 equals 3/2. Okay, f of -1 halves. So 1 point is going to be -1 3/2. Now let's evaluate 3. Let's evaluate f of 0. So f of 0, that's 3 times power of 0. 2 to the power of 0 is 1. That's 3 times 1. That's going to give us 3. Okay. Let me just put those points down here. Of halves. All right. Let's evaluate it at f of 1. 6, that point. Now, lastly, we need to evaluate it for f of, so f of 2, power of 2 times 4, 12, that point, 12. Okay. So again, we can plot these points, right? And the y-intercept occurs when we have x is 0. So the y-intercept would be writing it all y-intercept well, right? So the graph increases quickly as the base 2, which is greater than 1. Example number 2. Classify each as growth or decay and state the y-intercept. So we have two equations here. Let's start with g of x. So g of x is 5 and 1/2 with the power of x. So the base is 1/2. Since 1/2 is between 0 and 1, that's decay. And the y-intercept is the value of it. So essentially, a is equal to 5 half. So essentially, would occur 0 and 1. That's decay. Have a y-intercept 5. So very simple, straightforward. Now let's look at B. So when we're looking at B, we have h of x equals 2 per 1.4 raised to the. So 1.4 is greater than 1. So that's exponential growth. And the y value, or excuse me, the y-intercept is value of a. So in case 1.4 have greater than 1. That being said, we have a y-intercept. Uh, okay, so bases greater than 1 row, bases that are between 0 and 1, so decay. All right, pause the video and complete the problem at the bottom. Okay, so let's first of all start with the y value when x is equal to 0. So when x is equal to 0, y is 4. When x is equal to 0, y is 4. So a is equal, okay? So when y is equal to, or excuse me, we have x, matter of fact, it might be y two. Okay. So again, um, when x is equal to 0, y is 4. So a is equal, right? An exponential function for the table. So we have a equal to 4. Now we need to find common ratio, right? We'll find the common ratio. So the outputs are 4, 8, 16, 32. Now each value is multiplied by 2, right? 4 times 2 is 8, times 2, 16 times is 32. So that's very important. Values are multiplied by 2 to get the next value. So we can say that 8 divided by 4 is 2, divided by divided by is 2. So what does that say? That says that the base is 2, right? Now let's write the function. So this would mean that the function, in this case, 4 times 2 the x power. So this function starts here at 4 when x is 0, and then doubles each time increases, or each time x increases by 1. There's a double. Okay. Example number 3. A population is modeled by ET equals 1200 times 1.08 to the t power. So find p of 0, approximate p to the p x5, and interpret 1.08. So first of all, we need to find 0. What does that mean? That means substitute t equals 0. So when we have, or t 0 with 1200 power, um, that would be 0. That would be 1200 times 0 is 1200. So the initial population is 1200. Now let's find P of 5. So P of 5 is 1200 raised to the fifth. So we're going to approximate it using a calculator. So you could just put this in a calculator. That would give you 0.5. So since this is a population, we can round this. So you can round it to basically um, say 1760, and then the last part it says, and then interpret 1.08. So the base 1.08 means the population is multiplied by 1.08 each time period. So that means it essentially grows by 8%. So 1.0 a growth of 8% each time period. Okay. Now we need to do this. So essentially we have 1.08 equals same as 1 point or 1 plus 0.08. Okay. So that's why that the growth rate is 8%. So the model begins at 1200 and then grows by 8% per year. Look at it as like I said, 108%, talking about 8% more what the baseline was. Example number 4. So for this function, describe the transformation from this function, state the horizontal, etc. So first of all, let's write f of x, the power of x. Okay. Now I want to compare this with g of x function. We have x equals 2. Notice it's raised, parentheses, x minus plus 4. Notice the exponent is raised. So that means there's a shift here, and then there's also a shift there. So x minus 3 is inside the exponent. So that shifts the graph to the right 3 units. So x minus 3, right of 3. The plus 4, up 4 units. Then the parent function is f of x, power of x, right? And that has a situational horizontal asymptote of y is equal to 0. And after this shift happens, we have a y asymptote of y is equal. So the domain, negative, positive, so restrictions, so it's all real numbers. And then since the graph was shifted up, the outputs are greater than 4, right? So the range was 4 to infinity. The graph is shifted to the right 3 units, then shifted up 4 units. Then it has an asymptote of y is equal to 4, and the range that's greater than 4. What's a common mistake? Let's look at one. So a student says a table is exponential because the outputs increase. Explain why exponential change requires a constant ratio. So increasing outputs alone do not prove a table is exponential. So a linear function can increase too, right? The difference is the pattern. Linear functions have a constant difference. Exponential functions have a constant ratio. So you got to remember that. So linear, a constant difference, then a exponent has a constant ratio. So for example, kind of give you an example. So if I have 2, 5, 8, and 11, um, this increases by adding 3 each time, right? You see the sequence. So if I add 3, add 3, add 3, right? That's linear. So add 3, add 3, add 3. That's linear. Um, the difference, excuse me, let me see. This increases by adding 3 per each time. So yeah, that's linear. So um, the difference of plus 3 plus 3 plus 3, right? The difference of that, um, we'd say, but let's just say, for example, if we wrote 2, 6, 18, 54, right? So a difference of 3, difference of 3, difference of 3, right? A constant difference up here. And then down here, notice 2 times 3, 6 times 3, 18 times 3. So times 3 times 3 times 3. So what would we say? That's a ratio, right? That so this increased by multiplying by 3 each time. That's exponential, right? So this is a ratio. So a table is exponential only when the outputs are multiplied by the same number each time. Okay. When it's multiplied, there's a difference in addition. Okay. All right. So let's give a final review. All right. So as I said, we went over all these things and that we mentioned. The important thing you need to understand is that when b is greater than 1, that's growth. It's between 0 and 1. A. The y-intercept is 0 comma a. And the basic domain, you always want to think about the basic domain being negative infinity, positive. Then the basic asymptote is always y is equal. You always want to. Okay. All right. That concludes.